we'll finish off the graph problems. There are 2 problems left in that part, and then we'll go into the Sudoku. So the next problem that I want to show you is the vertex cover problem. So what is a vertex cover? So you're given a graph like left or right, and you have to find a subset of the vertices such that every edge is actually covered. And what is covered means that every edge is connected to one of these chosen vertices. Okay? So let's look at the left part. Okay? If so your task is to choose the vertices so that every edge is incident to one of these vertices. Okay? So let's actually do the extreme case. Suppose I choose only one node. So let's say I chose 1. Okay, does it cover the graph? Does it cover all the edges? Okay. When you color 1, then the edges that are covered is 1, 2, and 1, 3, because these edges are incident to the chosen vertex, right? But the other vertex edges like this one, they are not covered. So this is not good. Okay. So then let's add this one. Okay. Does it cover the graph? Still not yet, because these guys are not yet covered. So let's say we color this one. Does it cover all the edges? Why not? Because 5, 6, okay, so this edge doesn't have the chosen vertex, right? At least one of the endpoint must be chosen, but 5, 6 is not. So let's actually put this here. Okay? Now, do all the edges covered? Are all the edges covered? Do we have any leftover edges that are not connected to the red vertices? One of the red vertices? No. Okay, so we covered it. Okay, so this is a vertex cover of size 4, because we use 4 vertices. So computationally, what is a more interesting problem? To find a vertex cover of bigger size or smaller size? Smaller size. If you have a very extreme case, if you are allowed to use choose any set of vertices, I would actually choose all the 6 vertices. Then checking the cover is actually trivial. Every edge is covered by one of these vertices. So that's too easy. But if it is too small, then you are in the case that some edges may not be covered. So you have to find the minimal number of vertices such that this set of vertices cover all the edges. So the question here for the left one, what is the minimum size of the vertex cover? So we found 4. Okay, that means it could be up to 4, but maybe there's a chance that we can reduce this number, right? Can we try 3? Is it possible? So how do we choose? Erase 2. Let's say 1, 4, 5. Okay, so 1, 4, 5. Well, this covers, right? So every edge, if you choose every edge, this edge is covered, this edge is covered because of this. This edge is covered because of this. This edge is covered. This edge is covered. This edge is covered. This edge is covered. So every edge is covered. Good. So this is size 3. Okay. What about the right one? What is the minimum size vertex cover? What could be? Three. Okay, can you give one? 1, 5, 3. 1, 5, and 3. Okay, so let's check this. So let me use this guy. So here, this edge, so we have to check for every edge. So this edge is covered. This edge is covered because of this. This edge is covered. This edge is covered. This edge is covered. Yeah. Can you beat 3? Seems not possible. But how do you know it's not possible? In principle, you have to try all possibilities, right? If you have 2, then any pair, two vertices that you choose, you have to prove that there exists some edges that is not covered. Okay? And how many pairs of edges, vertices that you can do? This is 7, choose 2. Okay, so 21 possibilities. Did you do that by your brain? Did you try did you enumerate all 21 possibilities of the pair of the vertices and check for each of the cases that there is at least one edge that is not covered? You didn't do that. Computationally, that's what you have to do, but you didn't do. Okay? Well, of course, that's good because when the graph is simple, it's very intuitive, and you have some intuition actually helps you to check this quickly. But your intuition is actually easily get lost if this graph becomes big. It's hard to do that. Okay? So actually, in our lab, we try to do this kind of problem in neural network. If it is small enough, like humans, you can actually easily find the patterns that is not possible. But if it becomes big, then neural network suffers too. Anyway, so you are good at using intuitions. Computers are not good at using intuition. Nonetheless, if the size of the graph becomes big enough, then computers win. Okay? So you cannot catch up the computational speed in the computers. Okay, so then how can we solve this problem in Klingo? And what I'm going to show you is actually 4 lines of the code. Okay, so same as before, I will show you the English statement and try to guess what I would write in the next line. Okay, some of the lines, actually, by the last class, you already learned all constructs and all the programming idioms in the Klingo. So what I'm going to show you now are not really new. Okay, the new part is you are applying the same idea to different domains. Okay, and that requires some practice. It's like learning foreign languages. You can learn the grammars in one day, okay, but it doesn't make you fluent in that second language, right? You have to practice. Same as that idea. So the first one that we want to say is we want to choose subset of the vertices, and we will put that in the in predicate. Okay, so we are going to choose subset of the vertices. We did similar thing with the click. Okay, maybe if you remember what we did in the click is to find out some subset of vertices such that each pair of vertices have edge between them. Okay, so the first step is actually same as that. Okay, so we are going to choose subset of the vertices in the graph, and that is this line. Okay. So here, x is a local variable, and vertex x covers all the vertices in the graph. But we are going to select some of them and put it into the in predicate. And how many of them are we going to choose? N. Okay, so we'll choose a subset of the vertices whose size is n. That's what this line is doing. Okay? So suppose the number of vertices, the graph G has m vertices. How many stable models will be generated at this point? So m is a bigger number than n. Okay, we are going to choose a subset of the vertices. How many possibilities are there? This is called m chooses n. Okay? Actually, you can write this way. Okay? So m chooses n. When you learn discrete math, you will learn how to count these things. So let me not go over that. But if you have questions about it, welcome to ask on the piazza, and we can cover that. All right, so here we chose any subset of the vertices. The next one is we are going to define the concept of covered. Okay, this is the set of edges that have an endpoint in 1. Okay, so we'll say some edges are covered. How do we define the edges are covered? Okay, so first we write this way. Okay, what that means is if we chose this x, right, as a vertex, and if x is connected to y by an edge, right, then this edge is covered. Right? Recall the definition of covered. When is the edge covered? When this edge is incident to one of the chosen vertices. In of x represent those chosen vertices. So if x is incident to that edge, then we say that edge xy is covered. Are we done here? Are we not missing something? What about y? If y is in, we also need to say that that edge is covered. So this is the second line. Okay? So if y is in and there is an edge x comma y, then x comma y edge is covered. So we define covered based on the edge and in predicate. Okay, question. How many stable models will be there if I add up to this part? We did similar problem before. How many stable models will be there when I add these two rules? The number does not change because we are only define covered using the existing relationship. We are not introducing new models here. Okay, so when you add up, each stable model here that you found will be expanded with the definition of covered, but we will not create new stable models. Okay, if you think about this in terms of the possibilities, so what we did was chose a subset of the vertices, and then given the set of vertices, we actually add more information, but we are not actually changing each of the possibilities. Given the possibility, we can say some edges are covered or some edges are not covered. Okay? If you doubt about it, of course, you can check this when you run the Klingo. Okay? So, but for now, let's say that let's focus on understanding what this rule is doing. Okay? So choose a subset of the vertices, which has n elements there. And then we define that the edge xy is covered if x is in or y is in the chosen vertices. What should we do after this? We need to add more rules here, because what we did was basically we chose the set of vertices and we defined the concept of covered, but we didn't actually enforce that every edge has at least one, every edge is covered. We didn't actually formalize that yet, right? How do we write that every edge is covered? So that's actually the next one. Every edge should be covered. And this is one line here. So this is a constraint. Note here that at this point, we actually generate possible solutions. But these solutions may contain bad answers, right? Okay, this stable model may contain non-solutions to the original problem. So we have to prune out or weed out those bad answers. Okay, so what are the bad answers? The bad answers are the ones that satisfy this body. xy is an edge but it's not covered, then this is a bad solution that we have to prune out. Okay? So again, this is generate, define, and test part. We generate possible solutions, and we define the concept of covered, and using this concept, we prune out all bad solutions so that the remaining stable models will be the solutions to the original problem. Okay? It's actually one-to-one correspondence. Each stable model will encode the solutions to the vertex cover problem. Okay? Any question about these rules? Okay. All right, so then let's practice. So okay, so this is the rule that you just saw. And we had two graphs. What was graph .lp? Okay, so this is one of the graphs that we saw. Let me actually show you what that graph was. This is the graph. Okay? So this is the graph, and we have to find the vertex cover. Actually, we didn't do this exercise. What is the minimal size vertex cover for this example? Well, let's actually use Klingo, and let's come back to this one. Okay? So if you have some idea in mind, just pause, and let's see whether your guess was correct. So what I'm going to do is to call Klingo and vertex cover, and this was graph.lp file. And I don't know if I have to give the numbers. Okay, yeah. So I have to say what is the size of the vertex cover, right? So let's say, is it possible to have 3 vertices to cover all edges? Oh, it's not possible. Four. So this one, the minimal vertex cover is 4. So it says 1, 2, 5, 3. Let's go back. 1, 2, 5, 3. Okay? So if I have 1, 2, 5, 3, does it cover everything? Looks like. So every edge seems to be covered, right? Okay. So why not 3? Well, you can check. If you miss one of them, you will find at least one edge that is not covered. Okay. So, but how many possible choices are there? So we chose we show only one solutions, but how many of them are actually possible? There are actually 4 possible solutions. You can choose 1, 2, 5, 3, or you can choose 2, 3, 4, 6, or 1, 4, 5, 6, or 2, 3, 4, 5. There are actually 4 possible vertex cover of size 4. Okay, any question here? Okay. So this is just one solution, but there are 3 other solutions like this. Imagine that you have to write a program that find all vertex cover of some fixed size. It's not enough to find one solution. You have to find all solutions. What would you do? If you use Python, what would you do? You have to store all the information that you found, and you don't have to go back to the same one, right? So when you find one, you have to go again, not to choose the same solution, but choose different solution. And you have to iterate until you find no more solutions. It's not a very trivial programming to do, right? But here, when I show you this code, I don't have to worry about it, because that's what Klingo does for you, not that you have to program it. Okay? All right, so this is yet another graph. Let me just skip this. You can just run the same program on different graph instance. The rules are the same. The input to the Klingo to represent this graph instance is a bit different. All right, so the next one is called Hamiltonian Cycle problem. And what that means is you are given a graph, and you have to visit all the vertices, but you shouldn't visit the same vertex again, but you have to go through all the vertices. Okay, this problem is also known as traveling salesman problem. So you can imagine that each node is a city, and there is a road between the city, right? And the job here is this man has to travel all the cities and has to come back to the home, but we don't want to visit the same city again, okay? But also have to cover all the cities. Okay, so this is a problem. And as you can guess, this has enormous applications. If you look at the traveling salesman problem, if you Google it, find the papers, there are tons of papers to talk about how to find this Hamiltonian cycle efficiently. Okay? It's not a simple problem. It's actually much harder than the Sudoku problem. Okay? Well, this is actually not that big, so maybe you can use your intuition and find the solution. So let's do this together. Okay, let's say my home is here. Okay, so how shall we navigate this graph to visit all the cities? Anyone want to mention? So just tell me left to right, okay? Where should I go? Let's do row by row. How about any idea? Should we go left or right? Left, okay. What shall we do next? The second row, anyone? Should I go this one or this one? Down, okay. Next row. Right, okay. Next row. Up. Next row. Oh, you're not that row, right? Okay. The last row here. Yeah, you. The other way, which way? Left or right? Just tell me. So I'm here, left or right?
I guess I think we should go
left, okay. And then let's start with this first row. Where should we go? There are 4 people in the first row. Left? Okay, go to the left. Okay, then obviously we don't have any choice, so I'm not asking the next row yet. We have to go here, because if we go here, then we are violating the constraint. But now we have 2 choices, left or right, the second row. Some of you are already doomed, right? If it doesn't lead to the solution, it's not your fault, so don't worry about it, okay? We'll see what goes wrong here. I mean, it might have been the choice that some of the previous row has made affect you, right? It's not your fault, don't worry about it. Left or right?
Right.
Right, okay. And then the next. What shall we do? Anyone in the third row? Left or right? Right, okay. Then we have only one choice because we cannot go down. And now we have 2 choices, left or right? Left. Left or right? Mess up, okay. So what was actually the mistake? So obviously, again, this is not an easy problem. This is not too big graph, but still there are some choices that you have to make. If your choice is wrong, you have to backtrack and find the new solutions. So let me not waste more time on this. Let me just show you the solution. So what was wrong here was if you go this way, then there's no way that you can get to the solutions. Okay, this was a wrong choice. But how do we know that which choice is right or which choice is wrong? This is a hard problem. And it's actually unknown. Okay, so in many graph search problems, this kind of cases arises. You have to keep track of which choice that you have made. And if the choice was wrong, then you have to come back and try another choice. Okay, and that's how you write a backtrack search. Okay? And obviously, you may have learned in maybe some programming class, if you use the recursive programming, this kind of program can be easily solved, or easier to solve. Okay, but okay, so but let's use Klingo to solve this problem. Here is actually this, another instance that we are going to test, but let me just go into the Hamiltonian cycle encoding. So for this one, I need 1, 2, 3, 4, 5 lines of the code. So it's one more than before, so it's a bit harder, but hopefully you can get the idea. So what we want to enforce is there are actually two conditions that we want to enforce. So in the Hamiltonian circuit, we are trying to find the subgraph, okay, the node edge, okay, so all these passes that has these conditions. If you look at the solutions, okay, every vertex has only one incoming edge and only one outgoing edge. Okay, so let's actually look at the solution here, right? If you look at any vertex in the Hamiltonian cycle, okay, this is Hamiltonian cycle, right? It goes all the cities and come back to the original city. Each node has only one incoming edge and only one outgoing edge. If you have one incoming edge and two outgoing edge, this is not a Hamiltonian cycle. If you have no incoming edge, also this is not a Hamiltonian cycle, right? Okay? So every path has this property. Every vertex, for every vertex, there is exactly one incoming edge and one outgoing edge. That's one condition that we want to formalize in Klingo. But is it enough? If you just say, well, Hamiltonian cycle is a subgraph such that all the vertex has each vertex has only one incoming edge and one outgoing edge, are we done? It's not. What is the next condition that we have to cover? All points should be reached, right? Yeah. So it's possible that your graph is like this while there are 3 other cities that are not covered, right? If you have this one, each vertex has, actually, I should say this way. In this case, this is the whole graph. And each vertex has exactly one and exactly one outgoing edge, right? Same for these guys, right? But they are disconnected. So it cannot be a solution to the Hamiltonian cycle. So the second condition that we have to represent is every vertex is reachable from the home. If I chose this as a home, actually it doesn't matter which one that I choose as a home, but let's say this is the home, then every vertex should be reachable. But this case, this vertex is not reachable from the home vertex. So this is the best solution. We don't want to generate. Okay, so let me just repeat. What are the two conditions that we want to represent? Every vertex has one incoming edge and only one outgoing edge in the cycle. Second, every vertex is reachable in C from some fixed vertex, say home vertex, number 1. Okay? So we are going to turn this English description into the language of Klingo. So the first thing that we want to say is we want to say in xy is the set of edges included in the cycle. And we want to go further. We want to say that this satisfies the condition 1. So similar to the previous example, in predicate is used to choose some possibilities, right? In this case, in xy will choose some subset of the edges, right? Not whole edges, okay? But we are going to choose some subset of the edges. If you are very, very lucky, then maybe you will see that this choice will lead to the Hamiltonian cycle. Most likely, maybe not. Okay, so you have to enforce further conditions. So how do we write the rule that choose any subset of the edges and satisfies the condition 1? By now, when you think about subset, you should imagine, oh, there must be some local variable, and there must be some curly brace with the bound. Okay, so that's what I hope you have ingrained in your brain. So this is first rule. Okay, so you see there are two variables, x and y. Which one is global? Which one is local? Oscar?
Y is local, X is global.
Yes. So x has an occurrence outside the set brace. So this is a global variable, and y is local. And again, this is actually same code as you see from the representing functions, right? You use the x as domain and y as the range. So actually, it's not exactly the same, but it's similar to that. So what we are going to do is for each vertex, we are going to choose exactly one outgoing edge. Because edge xy means there's an edge from x to y, right? Okay. So for this one, if you fix any vertex x, then you should choose exactly one y to be in the in predicate. Okay? Okay, think about vertex as the giving the domain and edge giving the range. Okay, so for each vertex, choose exactly one y. Okay, and put it into in predicate. Okay, so in English it means that for each vertex there is only one outgoing edge. We also have to say about incoming edges. So the second one is saying that for each vertex y, there should be exactly one incoming edge. Okay? So that's what this in xy is representing. If you look at the in xy, these are the edges in the Hamiltonian cycle, supposed to be. Okay? So when you do this one, you're basically selecting the subsets of the edges that satisfies the condition that for each vertex there is exactly one incoming and one outgoing edge. Okay? So the structure of the program that I show today and last two classes is all same, right? So you start with generate part. Okay, so find some possible solutions and then prune out the bad solution. Sometimes we want to use the definition of some predicate. Now, if you look at this, what we are doing is simply finding the subset of the edges such that each vertex has only one incoming and one outgoing edges. It doesn't necessarily make the Hamiltonian cycle. So we are going to use this definition of reachability. And this is same as what you learned in mathematical induction. Okay, so some time ago we talked about the base case and inductive case. That is here as well. So the base case is this. We designated number 1 as the home city. So we say that any city that is connected by the chosen edge in 1, x, this x is reachable. Okay, so if x is 2, meaning that from city 1 to city 2 was chosen as the path in the Hamiltonian cycle, then we can say the vertex 2 is reachable, or city 2 is reachable, right? This is a base case. If you can go from 1 to the neighboring cities. The next one is a recursive case. In the recursive case, you're basically using the same predicate here and here. Okay? What it says is, if x is reachable from the home state, and there's an edge from x to y, then y is also reachable. Okay? And that makes sense, right? When we talk about reachability, which cities are reachable? Well, if you already know some city is reachable, and there's an edge from x to y, then y should be also reachable. Now, adding this one does not actually prune out any bad stable models. Same as before, this part is generating the possible solutions, but this one just adding more information to the solutions. But until now, we didn't say anything about this one. The second condition is not captured. Okay? And I said there are 5 rules, so I have only one rule left out. Now is your time to think about. What should be the condition 2? And let me actually open the Socrative. And you can talk with your neighbors if you have something to discuss. And the hint is it's very similar to the last line of the previous problem. Okay? The condition 2 here is every vertex has to be reachable, right? So in the vertex cover, the last line was saying every edge is covered. Now this time, I'm saying every vertex is reachable. Okay, there's some common structure between these two English statements. So in the test, I can give this kind of problems and make some other part written and ask you to fill the rule. Okay, I will give you English statement, so you can turn this into the Klingo rule. Okay. Okay, so let me open it. So these are the solutions. Let's see, edge xy not reachable y. I don't know. Okay, that's fine. In xy not reachable x. So you see various combinations possible. Okay. So the correct solution is actually this one. Okay? Why? So I said every vertex must be reachable, right? So let's actually come back to this, okay? So condition 2 is every vertex is reachable, every vertex. If it is not reachable, then it violates the constraint. Okay, so that's what we represent. So if you use edge, that's not actually what the second one is about. Okay, so if you use in, that's also not. Okay. Okay, so good. Actually, I should say actually, yeah, there are many people who actually answered correctly too. All right. Okay, so let's see whether we can do this problem. So this is the Hamiltonian cycle problem. Let's try this. If you start with one, now this is a bit easier than the first one that you saw. Maybe we can answer this. Anyone who wants to see what is the Hamiltonian cycle here? Or are we too lazy? So we just use Klingo to find it. Yes.
1 to 3.
1, 2, 3.
And then 6.
To 6. Unfortunately, if you look at this thing, there's an edge direction, so we cannot go.
Okay, 1 to 5.
So go to 5.
And then the 4.
And then 4.
And then 2 and then 6.
And then 2 and 6. But we have to come back to 1.
Oh.
So this one doesn't
From
work.
5.
You want to, okay, let me backtrack. Okay. So, Oscar, you want to try?
Yeah.
So let's start with 1,
1,
3,
5,
5,
6,
to 6,
2,
2,
4,
4, 1. Okay, so this is one solution. How many solutions will be actually there? That's actually harder problem, so let me not ask you on that side. So let's try this example. So this is Hamiltonian cycle program, and the graph is same as before. So this is the graph, okay? So we are interpreting this graph as a directed graph, okay? All right, so then we have Hamiltonian.lp, and this graph is graph.lp. So we found solution. Actually, how many solutions are there? There are actually 6 solutions. Okay, good. Okay, so then now let's go into the Sudoku problem. So, okay, anyone can solve this puzzle? What is the solution? This is the solution, and probably it takes some time to find it out. So let's actually use some smaller version, which maybe kids can also work on. So this is 6x6 Sudoku problem. But what I want to tell you is what is actually the strategy that you can use if you write a program to solve this Sudoku problem. Okay, so basically, the strategy that you have to use is when you have more constraint, then it's easier to find. The reason that I think some people like Sudoku is because it seems hard, but once you got into some level, after that, it just unfolds automatically. The answers are just folded out. So let's play with that. What would you do first if you see this puzzle here? By the way, for those who don't know what is Sudoku, so in this case, you have to fill the number from 1 to 6 to each of the cell, such that each row has exactly one number from 1 to 6. Same for columns and same for the box. Okay, so that's the condition. Okay, so what shall we do first? Which one? So let's actually call the coordinate so that to easily name it. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So what you're saying is 4, 6, right? This must be 5 because 1 through 6 has to be presented. So there are actually 6 numbers here. I mean, 5 numbers already filled in. There's no other choice. Okay, that's good. Now, the interesting thing is once you do that, then you also find another place that you can immediately find the answer. Which one is now? Which position? 4, 2. Okay, 4, 2. Now, if you look at the row condition, already 5 numbers are there. So the only number that is left is 6. Okay, good. And what next? Brandon?
You can put 2 at 1, 1.
2 at 1, 1. That's interesting because you're actually looking at the 2 conditions at the same time. So let's go slowly, okay? Let's imagine that we are a computer. We don't see the 2 things at the same time. We look at only 1 by 1. So let's look. So at this point, actually, it's not easy to see only from the 1 row or 1 column or 1 box, okay? So for that to work, you need only 5 other positions already filled in. But here we don't have that case. So let's look at 1, 1, for instance. If you look at the row condition, okay, so 4, 5, 1, 6 are used. So if you just look at only row condition, which numbers are possibilities? 2 and 3, right? 2 and 3. If you look at only the row, right? I told you that we are not going to use eraser, but we just need to put some scratch pad here, right? So I put 2 and 3, but then if I look at the other condition, I can even look at the box condition or the column condition. It doesn't matter, right? I can see that among these 2 choices, 2 or 3, I see 1 choice is not possible, right? Okay, that is 3, because I do have 3 here. So I cannot put 3 here, which means this must be 2. Okay, good. And once we do that, now we are coming back to the easier case. What is 3, 1? That should be 4. Okay, that's good. All right. And it also gives us another information. 3, 3 is 3, if you look at the row condition. Okay, that's good. Are we still lucky? Yes. Which place? 1, 6. What number do we have to fill in? 3. Okay, that's good. That's much better than before. As I said, when you do this, so probably the first non-trivial case was to fill 1, 1 because you have to consider 2 columns, but 2 conditions. But once you do that, there are more easier case pops up, so we can fill more. That's good. Are we still lucky? Doesn't seem to be, right? So that means we probably have to look into multiple conditions, but as if we are a computer, we don't look at the 2 conditions at the same time. Let's try to be dumb as much as possible here. So let's pick any position, 2, 2. Okay, let's go from left to right, okay? 2, 2. What are the, so let's actually look at the box condition first, okay? What is the number that we can put in 2, 2? What are the 2 possibilities? 6 and 1. 1 and 6. Okay. And now look at the column condition. What can I prune out? So 2, 2 has 2 choices, but now look at the column condition. You cannot put 6 there because the column 2 has 6 already, so this is not possible, which means you have only 1 here. Okay, we are back to the easier case. What is the number in 2, 3? What is number 2? 6, okay. But I know that some of you feel this is too easy, but try to help me, okay? All right, so are we still lucky? Maybe not. Okay, so let's go to the next left position. Here, 5, 2. Okay. So what are the numbers that I can fill in here? If I look at the column, I have 4 numbers already filled in, and 2 and 3 are not there yet, right? 2 and 3 are not there. Okay? But as soon as I have 2 and 3, I know that one of them is not actually possible if you look at another condition. What is that? Yes, 2 is not possible because if you look at the row condition, 2 is already here, so 2 cannot be there. So we just cross out. Then you have 3 here. Then it's easy. This must be 2. Good. And then it's also easy if you look at this. What is 5, 3? 4. Okay, now what is 6, 3? 1. Yeah, good. Okay, good. Are we still lucky? Not quite. Okay, so then let's go to the next one, which is 2, 4. Okay, so 2 choices possible. What are the 2 choices? 4 and 5, right? Okay, let's look at the other conditions involving this position. Are we still good? If you look at the columns, okay, can we actually get anything pruned out? Unfortunately not. Okay, this time I don't see how to do, but what I know is at least this one is also either 4 or 5. Right? That I know. But I don't know. I mean, I don't see any other things that I can do at this point unless I'm missing. So this one I will just hold. I will move to the next position. So let's go to 2, 5. What are the 2 choices that I can put here if I look at the column? 3 and 5. Okay. Now, look at the other conditions involving this position. What can be? Do we have any pruning out? Look at the row. The row already has 3 here, so this 3 is not possible, which give me 5. And at this time, I can also say that 5 is here, then this is not possible, which means that this must be 4. If this is 4, then this cannot be 4, so this is 5. Good. So this is the fun when people do Sudoku. You just do one thing, and then you just fill immediately, right? Okay, so the next one is 2, 6 is also easy. This must be 2. And 6, 5 is 3, right? And then 6, 6 only left is 4. This is a solution. So we solved 6 by 6 Sudoku. Congratulations. Yeah. All right. And the idea is actually not too much different. If you go to 9 by 9 Sudoku, it's actually the same idea. You don't have to use eraser. You may just need to write this and then cross out. That's what people do. There's some strategy, of course, that helps you to find this more quickly. Okay? But even if you're dumb, or like computer, okay? Computer doesn't look at the multiple conditions at the same time. You can solve this puzzle, okay? Using very simple algorithm. Okay, so how do we solve the Sudoku problem? Okay, so the first one is, this is actually probably most difficult part of the formalization. So you have to place the number 1 through 9 to one cell in each box. How many boxes are there? If you think about standard Sudoku, which is 9 by 9. No, box, not the cell. There are 81 cells, yes, but how many boxes are there? Each box contains 3 by 3. So then how many boxes are there? 9, okay. So for each 9 by 9 box, we have to place, so suppose we have this thing, okay? So 1 through 9 should be placed in each of the box. That's what we do as a generate part. How can we generate this? Just to give you a warning, if you don't understand this at the first sight, that's okay. It takes some time to understand this line. And there are also other ways to represent this condition, maybe a bit easier to do. But this happens to be one of the fastest solutions that previous student found. So we are going to look at that solution. Okay? Actually, some time ago when the computers were slow, we have this competition. So everybody was writing Sudoku puzzle, and we have competition whose Sudoku program runs fastest. Unfortunately, hardest Sudoku these days are not really that hard. So, all right. So the rule that I'm going to write is this one. Okay, it's a quite heavy line. What are the global variables? What are the global variables in this program? Yeah, n, x1, y1, they are the global variables. And what are the ranges of these global variables? N can range from 1 to 9, right? How about x1 and y1? What are their range? What are their values? So 0 data 2 means 0, 1, 2, right? And these are multiplication plus 1. So what are the possible values of x1 and y1? 1, 4, 7, yes. When it's 0, it's 3, 0 plus 1, which is 1. When this interval gives 1, then 3, 1 plus 1 is 4. When the interval gives 2, 3 times 2 plus 1 is 7. So what you will see is that the global variable n range from 1 to 9, and another global variable x1 range over 1, 4, 7, and same for y1. Okay, so let's keep that in mind. Okay, and roughly what this is saying is for each number, and this gives us which box that we have to look at. Okay. So the combination of x1 and y1 gives one of the 9 boxes. Okay? So when x1 is 1, y1 is 1, that represents the first box over there. Okay, the left top box. Okay? When x is 4 and y is 1, it represents the second box on the right. Okay? And so on and so forth. So we'll actually go over that more carefully. But roughly the idea is you have one possible, one number from 1 to 9, let's say 5, okay? And then you have one box, let's say the first box on the left top. Then you have to find one position from that box. That's what the rule is saying, okay? So let's try to give some informal reading first. So when you have these global variables, fix some values, okay? So fix, let's say, n equals, say, 1, and fix x1 equals, say, 1, and y1 equals 1, okay? Then what this rule is saying is the x will range from 1 to 1 plus 2, which is 3. The x here will range from 1 to 3. The local variable x will range from 1 to 3. And local variable y will also range from 1 to 3. Okay? So this is y1. y1 is 1. And y1 plus 2 is now 3. Then this y, in between 1 and 3, the local variable will range over 1 to 3. Okay? This is actually just to make the rules to be safe, but it's not actually essential meaning here. Okay, so what it means is you are going to, given the possible value of n, we are going to select x and y position, where x goes from 1 to 3 and y goes from 1 to 3. Okay? So this is what I just said. If n equals 1, x1 equals 1, y1 equals 1, the rule there is simply saying this. Given the digit 1, you have to find exactly one pair of xy, where x goes from 1 to 3, y goes from 1 to 3, which is denoted by the top left box. In the top left box, the x coordinate goes from 1 to 3, and this goes 1 to 3. Okay? So you have to find exactly one position to put digit 1. And this will be repeated with different values of n. When n equals 2, again, you're putting number 2 or digit 2 in the first box. Same for 3, 4, 5, 6. So when x1 equals 1 and y1 equals 1, and when n goes from 1 to 9, this means that for each values of n, put it in the first box. Okay? That's what this rule is about. Again, this is a bit complex rules. Okay? The best way that you can understand this is, as I just showed you, instantiate the global variables and try to understand from there. Okay? If you have difficulty, let me know. Okay? Let's actually show one more example. When n equals 5 and x1 equals 4 and y1 equals 7, which box are we looking at? So here we have to place number n, 5, digit 5, into the one box here. But when x1 equals 4 and y1 equals 7, which box are we looking at? So it will be instantiated since x1 is 4, 4, 5, 6. So x will range over 4, 5, 6. Y1 is 7 there, then 7, 8, 9. So y will be ranging over 7 to 9. So that will be 4, 5, 6, 7, 8, 9, this box. Okay? Basically, let me actually write this way. So if you have this box, and if you only count x1, y1 pair, okay? So there are actually 9 sub-boxes. So here, when x1 equals 1, 1, it'll be here. Okay? So when x1, y1 is 1, 4, then it represents this box. And this is 1, 7. Okay? When x1, y1 is that value. Okay? So this will be 4, 1, 4, 4, 4, 7. Okay, so this coordinate that I write is the values of x1 and y1. When x1 is 7, y1 is 7, then we are looking at this box, and we have to place numbers from 1 to 9 in each of these cells. All right, any question here? This is the most difficult part, and once we do that, the rest is easy. Okay, what are the rules that we have to say? No two different columns given a row and a number. Okay, so given this row number and the digit, we shouldn't have the same numbers on this on that row. Okay, so suppose you have the same row x and you have the same number n in 2 different columns that violate the constraint. Okay. Similarly for the row condition. Okay, so if you're given a column, you cannot repeat the same numbers. That's also written this way. Okay, so here you see that column ranges from 1 to 9, row ranges from 1 to 9, and the number range from 1 to 9. If you're given the 2, okay, then you should not have the 2 different numbers for the third dimension. Okay, and this constraint is actually similar to the constraint that we saw in the Queen's problem. Okay. Okay, so let's actually see how do we solve Sudoku problem. I think this was actually the last thing that I didn't mention. These are the general rules, but we have to actually talk about the instances. So we are given some instance, and 1, 1 position we have number 9, 1, 5 position we have number 8, and 1, 7 position we have number 3. So these are the instances. It is dependent on the particular instance that you see. Okay. All right. So let's see. I have Sudoku here. Sudoku.lp. Okay, so this is the program that you saw. As I said, actually it involves 4 lines of the code. But also we have the Sudoku instance. So this is the instance. Okay. So A 2,7,7 means at the position 2,7 there is a digit 7, and so on. So this is what you can do. And how do we solve this problem? You give the rule Sudoku and also Sudoku instance. Then you found the solution. It takes 0.024 seconds. If I ask to find all solutions, it's still the same because usually there is only one solution in the Sudoku. Okay? All right. So our time is almost up. So let me actually just show you something that you will probably do for the homework. So this is something that I found from the internet. I think it's a bit nonsense to me, but this is so-called world hardest Sudoku. Okay, so try to solve by yourself. If you got stuck, the homework problem is asking you to solve this using these rules that I gave you. Okay. To me, actually, this is harder. 16 by 16 Sudoku. Okay, so numbers from 1 to 16, 4 by 4 boxes, and so on and so forth. I don't think this will take that much time in Klingo. In fact, actually, even the hardest Sudoku, I don't think it will be taking more than 0.5 seconds. Okay? And similarly for this, it doesn't seem to be that hard. Okay? I have actually a few other variations of Sudoku, so I'll continue this next time. Okay, any question about today's material? Okay, then let's close the lecture and open the exit ticket.